Hi, we continue the 8.3-8.4 testing contingency tables. We have another test. So that is Fisher's exact test. So Fisher's exact tests test the same hypothesis as chi-square test, but more accurate when the numbers in cells are small. So chi-square test, often it's claimed that if expected value is less than 5 for some cells, then approximation by chi-square distribution that isn't very accurate. And Fisher's exact test is based on slightly different assumptions, but basically it calculates exact probability. So for a small table, it's considered as a more accurate. And the idea is here. So it calculates the probability for each table, given the marginal counts Ri for the ith row and the Cj for the jth column under independence. So for each table, we calculate the probability and that we see how plausible it is. So if we have, for example, the 6 possible tables for given the marginal counts and the row counts and the column counts, and that we calculate the probability for each table, such as the 0.01 and the 0.02 and the 0.07 and the 0.2 and the 0.3 and the 0.4. Okay, then this T1 is the most extreme. Maybe T2 is also extreme. So if we use the 5% threshold, the T1, T2 are extreme table, and the others are just the usual table. So we define the T1 and the T2 as the significant, so that we reject the null hypothesis that two factors are independent. And yeah, so that is the table. But to explain the Fisher's exact test concretely, we will have a small example. So we want to test this if this factor A and factor B are independent or not. So we have only 6 observations, the A, B, C, D, E, maybe E, F, and we have these numbers of observations. And anyway, we only have 6 observations, so it's hard to say. But if we compare the ratio, this is 0 to 3 and 2 to 1, so possibly A and B are dependent. So we want to test. Then the idea is that at first we fix marginals. So the marginal counts is 3, and 2, and 4, in total 6. Okay, and at first we calculate how many tables are possible given marginals. How many tables are possible given marginal? How many? Maybe I would say that how many ways to put 6 observations given marginal. So given marginal, that means the given this 3, 3, 2, 4. So if we have 6 observations, A, B, C, D, E, F, then we have to assign. So okay, so think about the rows and the columns separately. So at first, think about rows. Then basically, we have to assign the 2x out of these 6. So maybe B and D are x. And also columns. We have to assign the 3 z's here. So we have to assign 3 z's. So maybe this is z, and this is z. So 2 out of 4 for rows. So that is in total the 6 combination, the 2 ways to assign the 2 x's. And the second one, the 6 combination, 3 ways to assign the 3 z's. And the 6 combination 2 is the 6 factorial, 2 factorial, 4 factorial. And this is actually the 6. This is 15. And the combination 3 is the 6 factorial divided by 3 factorial, 3 factorial. So this is the 6 times 5 times 4, so 120. Not that, the 6 times, and the 120 divided by 6, so that is 20. So in total, the 15 times 20, so rows and the columns are assigned independently. So the 15 times 20. So 300 ways to achieve this marginal density given 6 observations. So in total, we have 300. Then we think about how many of them makes this table T1. And also the other possible tables we consider. So given marginal, so marginal numbers should be this 3, 3, 4, 2, 4. And actually 3 possible tables, because if you determine the upper left cell, that was 0 in the first table, but if we put 1 in this table, automatically other numbers are determined because marginals are given. And if upper left is 2, then this is 1, 0, and this is 3. And the z cannot exceed 2 because the row total for x is 2. So we only have the 3 tables. And how likely each table happens. So we want to calculate this. And then how many ways to make this table 1? T sub 1. Then we have the 0 to 3, 1. So in total, we have the 6 observations. Right? So we have basically we choose the 0 observation here, and we choose 2 observation here, 3 observations here, 1 observation here. So that is the multinomial, the case. So the total number of ways to put A, B, C, D, E, F in this way is the 6 factorial divided by 0 factorial, 2 factorial, 3 factorial, 1 factorial. So if we have 2 terms, this is combination. But if we have the multiple terms, that is this number. Yeah. So this is a kind of so just we can just so we can assign the 0 observations. Yeah. So 0, 2, 3, 1. So we can calculate this as the number of ways to get T1. And this is the 6. Okay, so 6 times 5 times 4, and the 3 factorial cancels with the denominator, and just 2 factorial in the denominator. So this is the 6, 5, 4 divided by 2. So that is the 3 times the 20. So this is 60. So we have 60 ways to get the table 1. And how about other 2 tables? How many ways to get the T2? So T2 sounds most typical table given marginal, because everything is proportional to marginal distribution. And actually the number of ways is equal to 6 factorial, and we choose 1 observation for upper left and 1 observation for upper right, and 2 observations for lower left and 2 observation lower right. So this is equal to the 6 times 5.4 and the 3 to 1 and divided by 4. So this is 180. So we have 180 ways. So this is more plausible table. So this is 180, this is 60. And you can calculate the last one. And the last one actually the same as the first one in terms of the number of ways to make this table. Because the last one, the T3, this is the 6 factorial. And again, the 2 factorial, 0 factorial, 1 factorial, and 3 factorial. So this is again the 60. And the 60 observations, so 60 here. So now that we can calculate probability. So in total, we have 300 ways, the 60 plus 180 plus 60. And the first one is 60 over 300. So probability is 0.2. Okay, so this over 300. So this is 180 over 300, so 0.6. And this is 0.2. So the p-value for this table, table 1, p-value for table 1 is equal to the summation of probability of this and the smaller. So that means this is 0.2. So, and the last one is as extreme as the first one. So p-value is 0.2 plus 0.2. So p-value is 0.6. So next one is actually have the largest probability. So p-value is 0.2, 0.2, 0.6. So no table is less extreme than this. So p-value is 1. So often the Fischer's exact test, we get p-value of 1. And the last one, the same as the first one. So p-value is 0.4. So, oh, sorry, the first one 0.4 also. So the 0.4 is p-value. So we do not reject the null hypothesis of independence for A and B. So this is how the Fischer's exact test works. Yeah, so the general procedure is here. So we are given the subtotal of rows, that is Ri, and subtotal for j's, that is the Cj's. And this is the total number of ways to align to get the specific table, the Oj. And the denominator is the total number of ways for Ri and Cj. So to achieve that marginal distribution, that we have this combination. So this is just a generalization from the previous one. So last time that we multiply 6. So the combination, this is the 6 choose 3, and the other one, the 6 choose 2. And we generalize it into the multiple rows and multiple columns and the general numbers. And the numerator is just all possible combinations. So that we have this demonstrated in the previous page. So if we cancel the several terms, for example, the n factorial is here and here, so we can cancel it, then we can simplify it to this expression. So this is the formula to calculate the probability of a specific table, the T0. Then we sum up all probabilities, which is more extreme than the T0. Okay, so then we can calculate the p-value. So this is how the Fischer's exact test is implemented. And one thing we have to mention is that we get p-value directly from the data. So the z-test, we calculate the z-statistic, and the t-test, we calculate t-statistic. Chi-square test, we calculate chi-square statistic. But the Fischer's exact test, we directly calculate the p-value. So we don't have intermediate product to test. And here is an example for Fischer's exact test. So D is the hair color, eye color data. So it's the same as the chi-square test example. And just the Fischer.test function do Fischer's exact test. Since we directly calculate the p-value, actually the output is only the p-value. And alternative hypothesis, the two-sided. So that is almost always two-sided. And this is similar to chi-square test. Yep, so the obtained p-value is 0.0463, and this is close to the chi-square test. So even though the chi-square test is claimed that the approximation is not good for a small table, but mostly we can get the same number. And the more important thing is that the Fischer's exact test is time consuming, so that we calculate the exact probability, and you can see from the example the handwritten example, it takes a lot of time to calculate all the probability of that table, therefore all tables. So it doesn't work for very large tables. So if the numbers are 10 or even 30 or 50, then still it's plausible to do. But if the numbers are large, anyway, the chi-square test isn't different from the Fisher's exact test much. So you can use the chi-square test.